Good afternoon, students. Welcome to the lecture on Basics of Electrical and Electronics Engineering. Myself, Srimati Roopa M, Selection Grade Lecturer, PVP Polytechnic. Let us begin this 15th session. We'll deal with the chapter Electric Motor Drives. So today we'll learn about AC motors. So under this, we will learn types of AC motors, single-phase AC motors, three-phase AC motors, selection criteria of AC motors, and its applications. So what is the meaning of drives? Systems employed for motion control are called as drives. It may employ any of the prime movers, namely diesel engines, steam turbines, and electric motors for supplying mechanical energy for motion control. Drives employing electric motors are called as electrical drives. AC motor. Let us define what is an AC motor. It is a motor which converts alternating energy into mechanical energy. So it is a motor which converts alternating current energy into mechanical energy. An AC motor is an electric motor driven by an alternating current. So electrical energy in the form of AC is converted into mechanical energy. What are the different types of AC motors? AC motors are broadly classified as induction motors and synchronous motors. This is the classification of AC motors. So you can see here, AC motors are classified as synchronous motor and induction motor. Induction motor further are of two types, single-phase induction motor and three-phase induction motor. So this is the structure of a it has a stator. Stator is the stationary part of the motor, and this is the rotor. Rotor is the rotating part of the motor. Now this is the parts of an AC motor. So here it is in section. You can see here. Now this constitutes the stator, that is the stationary part. Here in the middle, you see the rotor. These are the bearings. There is a fan fitted on the same shaft as the rotor. It's a cooling fan. This is the frame or the yoke of the motor. Now this is the exploded version of an AC motor. So you can see all the different parts here. So here, and this is the fan cover. This is the cast iron frame. Here is the rotor. This is the shaft, the bearings, the bearing locks, and this is the end cover of the motor. Let us learn about induction motors. Induction motors are alternating current motors which convert alternating current electrical energy into mechanical energy. They work on the principle of induction. They are also called as asynchronous motors because it always runs at a speed lower than synchronous speed. Synchronous speed means the speed of the rotating magnetic field in the stator. So what is the working principle of an induction motor? Induction motor works on the principle that whenever a closed conductor is placed in a magnetic field, it experiences a torque. A torque is a rotating force. It is a twisting moment or a rotating force. So, whenever a closed conductor is placed in a magnetic field, a current carrying conductor is placed in a magnetic field, it experiences a torque. It works on the principle of induction, where the electromagnetic field is induced into the rotor when rotating magnetic field of the stator cuts the stationary rotor. So you have to understand here, inside the stator, it has the armature windings there. So when a current passes through the armature winding, when it is energized, it sets up a magnetic field. Now this magnetic field, when it cuts, which is rotating in nature, this magnetic field is rotating in nature, and when it cuts the stationary stator, it induces an EMF in the rotor. And because of this, a current flows through the rotor conductors. Now, what is torque? Torque of an induction motor is the rotating force or the twisting force experienced by the rotor conductors about the rotor axis. It is denoted by T and is measured in Newton meters. Now, what is the basic principle of working of an induction motor? We have already studied, in case of DC motor, supply is needed to be given for the stator winding as well as for the rotor winding. So in the previous class, we have seen that a supply has to be given to both the stator and the rotor. But in case of an induction motor, only the stator winding is fed with an AC supply. Alternating flux is produced around the stator winding due to the AC supply. So you have to recall here, any current carrying conductor sets up a magnetic field around itself, which is the Oersted law. So in the previous class, we have learned that. So an alternating flux is produced around the stator winding due to this AC supply. Now this alternating flux revolves with synchronous speed. The revolving flux is also called as the rotating magnetic field, RMF, rotating magnetic field. The relative speed between the stator RMF, that is the rotating magnetic field, and the rotor conductors causes an induced EMF in the rotor conductors according to the Faraday's laws of electromagnetic induction. So we have already learned Faraday's laws of electromagnetic induction. The first law states that whenever a current carrying conductor is cut by the flux, an EMF is going to be induced in it. The rotor conductors are short-circuited and hence rotor current is produced due to this induced EMF. So here you can see the figure. Now this is the stator, which houses the stator windings. This is the rotor, which is free to move. Stator is the stationary part. Rotor is the rotating part. So the rotor also carries conductors. You can see on its periphery. It has the conductors are placed on the rotor. So when the stator windings are energized, that is when a current flows through the stator windings, it sets up a magnetic field as shown by these dotted lines. You can observe here, it sets up a magnetic field. Now this magnetic lines of force or the magnetic flux, when it cuts the rotor conductors, since this magnetic field is rotating in nature, since the magnetic field is rotating in nature, when it cuts across the rotor conductors, an EMF is going to be induced in the rotor conductors. Since the rotor conductors form a closed path, an induced current is going to flow through the rotor conductors. So here you can see the action of these flux on the rotor conductor. So here you can observe the two rotor conductors which are shown here are subjected to a twisting moment or a rotating force called as the torque. So you can see here this conductor tends to move downwards. You can follow the arrow here. It tends to move downwards, and this conductor here is being pulled upwards. So this is moving downwards, whereas this conductor is trying to move upwards. That means a rotating force or a twisting moment or torque is set up in the rotor, and hence the rotor starts rotating. Now, the induced current in the rotor will also produce alternating flux around it. So we have learned that any current carrying conductor sets up a magnetic field around itself. Now, in the air gap, there are two magnetic fields. One is due to the stator windings. Another is due to the rotor windings. The difference is this rotor flux. The direction of the induced rotor current, according to the Lenz's law, is such that it will tend to oppose the very cause of its production. As the cause of production of the rotor current is the relative velocity between the rotating stator flux and the rotor will try to catch up with the stator rotating magnetic field. So, stator rotating magnetic field is ahead of the rotor flux. That means the rotor flux is always lagging behind the stator flux. There is a relative velocity difference between the two fluxes, and always the rotor flux tries to catch up with the stator flux. Thus, the rotor rotates in the same direction as that of the stator flux to minimize the relative velocity. That means it tries to catch up. The rotor starts rotating in the same direction as the stator flux, and it tries to catch up with the stator flux. But however, the rotor never succeeds in catching up the synchronous speed. Synchronous speed is the speed of the rotating magnetic field. So, rotating magnetic field is being set up by the current flowing through the stator windings. So that is setting up a rotating magnetic field. So the speed of that RMF is called as the synchronous speed. So the rotor never succeeds in catching up with the synchronous speed. Now what is synchronous speed? The rotational speed of the rotating magnetic field is called as the synchronous speed. It is represented as ns and is given by the equation 120 F by P. It is expressed in RPM, where F is the frequency of the supply in Hertz. P is the number of poles on the stator. What is rotor speed or the actual speed? It is represented by N. The speed at which the rotor rotates is called the actual speed. So one is synchronous speed is speed of the rotating magnetic field. Now where is this rotating magnetic field? It is set up by the stator windings. How is it set up? Because of the current flowing through the stator windings, a magnetic field is set up which is rotating in nature, and the speed of that is called as the synchronous speed. Rotor speed is the actual speed. It is the speed at which the rotor is going to rotate. So it is denoted by N and it is measured in RPM, rotations per minute. Slip. Slip is represented as S. The difference between the synchronous speed and the actual speed is called the slip. So there are two speeds here. One is the synchronous speed because of the rotating magnetic field of the stator winding. Another is the actual speed because of the rotor. Now the difference between these two speeds is called as the slip. Now it is usually expressed as a fraction of the synchronous speed. To get the fractional slip and as a percentage of synchronous speed, to get the percentage slip. So in different forms you can express. Slip is equal to synchronous speed minus actual speed. So difference in, we have stated here, difference between the synchronous speed and the actual speed is called slip. So slip equals synchronous speed minus actual speed. Synchronous speed is represented as ns minus n, which is the actual speed, and the unit is RPM. Fractional slip is given by the equation ns minus n, that is the difference between the synchronous speed and the actual speed expressed as a fraction of synchronous speed. ns minus n divided by ns. And percentage slip is given by ns minus n divided by ns into 100. So this will give the percentage slip. There is no unit for slip. You have to understand why slip is important in an induction motor. The rotor tries to catch up the synchronous speed of the stator field and hence it rotates. But in practice, the rotor never succeeds in catching up. If the rotor catches up with the stator speed, then there won't be any relative speed difference between the stator flux and the rotor. Hence, no induced rotor current and no torque production to maintain the rotation. This will cause the slip to be zero. Then the motor will be at standstill. So the motor, the speed of the rotor starts decreasing and it may come to standstill. Therefore, an induction motor cannot run at synchronous speed. That is why the rotor rotates at a speed which is always less than the synchronous speed. So it will never catch up. If it catches up, then there is no relative difference in speed between the two fluxes, that is the rotor flux and the stator flux. Then there will be no induced EMF, no induced current, and no torque production. Therefore, then the motor will stop working. Therefore, the rotor always rotates at a speed which is always less than the synchronous speed. Types of induction motor. Based on the number of phases, induction motors are classified as single-phase motors and three-phase motors. Single-phase motors run on single-phase supply and three-phase motors run on three-phase supply. Now, what is the difference between single and three-phase motor? Single-phase motors need less maintenance when compared to three-phase motors and it has longer life. Single-phase motors are typically used in devices and equipments that require lower levels of horsepower or when it is inefficient to use a three-phase motor. Single-phase motors have a similar construction to a three-phase motor, including an AC winding that is placed on the stator and the short-circuited conductors that are placed in a cylindrical rotor. The biggest difference between the two motors is that with the single-phase motor, there is only one phase supply to the stator, whereas a three-phase motor has three-phase supply. Three-phase induction motor. This induction motor works on three-phase AC supply and work on induction principle, and hence they are known as three-phase induction motors. There are two types of three-phase induction motor, namely squirrel cage induction motor and wound rotor induction motor. These are also called as phase wound induction motor or slip ring induction motor. So they are of two types. One is the squirrel cage induction motor. Another is the wound rotor or the slip ring induction motor. Now, let us see the constructional details of an induction motor. An induction motor, whether squirrel cage or wound rotor type, mainly consists of two parts, that is the stator and the rotor. These two are the main parts of the induction motor. The stator contains the stator frame, stator core, stator windings, end shields, bearings, and brushes. While the rotor contains shaft, rotor core, rotor winding and the slip rings. So this is the construction of a induction motor. This is the frame. The outermost is the frame, which is made up of cast iron. It gives mechanical support for the stator as well as the rotor. It protects the inner windings. Here on the inner periphery of the stator, you can observe a number of slots are cut. So inside the slots, these are called as the stator slots, and inside the slots, the stator winding is going to be placed. Now this is the stationary part of the induction motor. Here in the central region, you can observe there is the rotor. The rotor has a number of slots cut on its outer periphery, and in the slots, so these are the rotor slots, and in the slots the windings, the rotor winding is going to be placed. Now there is the central shaft on which the rotor is going to be placed. The rotor drum is going to be placed. Now these slots are made up of a number of laminations. As we have already studied what are laminations in the transformers as well as in the motors. We have studied what are the laminations made out of. It is usually made out of silicon steel. A number of thin stampings are stacked together and riveted or bolted together, and it forms the laminations. Laminations are done to reduce the eddy current losses. So here is the air gap between the stator and the rotor. So when these stator windings are energized means when it is connected to a supply. So if it is a single phase induction motor, it will be connected to single phase supply. If it is a three phase motor, it will be connected to three phase supply. So in general, when the current flows through the stator windings, as per the Oersted law, we know that any current carrying conductor sets up a magnetic field around itself. So all the stator windings set up a magnetic field, and this magnetic field is rotating in nature. And when these rotating magnetic field cuts across the stator rotor windings here, when it cuts across the rotor windings, it will cause a torque. Torque is a twisting moment or a rotating force. Therefore, what happens here is some of the conductors will be tried to be pulled downwards, while the other half of the conductors here will be tried to be pulled upwards. Because of this, a rotation in the rotor occurs, and the rotor starts rotating, and it will try to catch up with the rotating magnetic field of the stator, but it will never succeed in catching. So there is always a relative speed difference between the stator flux and the rotor flux, which is called as the slip. So these are the different parts. So here you can see the stator yoke windings, stator core. This is the terminal box to bring out the windings. So this is the eye bolt to handle the machine. And here is the squirrel cage rotor here. This is the slip ring or the wound rotor. Now let us study what is a stator. Stator is the rotating part of the induction motor. It is common to both squirrel cage and wound rotor induction motors. The stator windings are similar to the armature windings of an alternator. They are wound for required number of poles. So it depends what is the number of poles in the machine, whether it is 2, 4, 6, 8 like this. Depending on that, there will be the number of windings, the conductors in the stator windings. Now the constructional details and the function of each part of the induction motor is similar to that of the stator of an alternator. So we have already studied alternator or the AC generators. So the construction is very much similar here also. The stator frame is made up of casting materials. It provides mechanical support to the stator and the rotor. The stator core, it is built up of high-grade alloy steel or silicon steel laminations or stampings to reduce the eddy current losses. So very thin laminations of around 0.35 mm to 0.5 mm are cut in silicon steel. So a number of them are stacked together and they form a solid stator core. Its main function is to carry the alternating magnetic field. The stampings are fixed to the stator frame. Each stamping are insulated from the other with a thin varnish layer. The thickness of the stamping usually varies from 0.3 mm to 0.5 mm. Slots are punched on the inner side of the stamping. So just now we have seen the construction here. Slots are punched on the inner periphery of the stator. Stator windings. The core of the stator carries the three-phase windings which are usually supplied from a three-phase supply system. The 6 terminals of the windings, 2 of each phase. So there are 3 phases, R, Y, B, red, yellow, blue. So there will be 3 coils. Every coil has got 2 leads or terminals. So totally there are 6 terminals of the windings, 2 of each phase. So every phase will have 2. R contributes 2, Y has 2 and B has 2. So 2 plus 2 plus 2, that is totally 6 terminals are there which are connected in the terminal box of the machine. Wound for a definite number of poles depending on the speed of the motor. So what speed we require, based on that will be the selection of the pole. So you can here observe from the formula, the speed is inversely proportional to the number of poles. So this is given by the equation ns, which is the synchronous speed, is equal to 120 F by P. So speed and the number of poles is an inverse proportion. That means if you increase the number of poles, the speed of the machine decreases. The speed of the machine increases. So the choice whether we want bigger speed or a smaller speed, based on that the number of poles will be decided. So if the number of poles is greater, the speed of the motor will be less. And if the number of poles is less, then the speed will be high. So based on the application, the choice will be made for the number of poles. Now this is the stator construction. So here this is a stator stamping. You can see here. So a number of slots are cut on the inner periphery. So this is a circular ring like. This portion is known as the inner periphery. This is the outer periphery. On the inner periphery, number of slots are cut. Now this rotor stamping itself is a very thin lamination, around 0.5 to 0.5 mm, 0.3 to 0.5 mm. Inside this slot, the windings will be placed. This projecting portion is called as the tooth, and this is the slot. So you can see a variety of slots can be engraved into the stamping. And observe here, this entire stator is made up of a number of such stampings stacked together. Stacked means placed one above the other and bolted or riveted together. So you can observe here. You can observe these bolts here. You can see the bolts. This looks like one solid piece, but actually a number of stampings have been placed one above the other and they are bolted together. And inside the slots, can you observe the slots here? So inside the slot, the winding is going to be placed. So this is still the starting. After completing, this is how it looks. This is the stator winding. So you can see here the copper color here. This is the windings here. So this is a three-phase induction motor. This is the stator. This is the slots, and these are the stator windings placed inside the slot. So this is how it is done. Next, we'll understand the construction of the rotor. Rotor is the rotating part of the induction motor. So the three main parts of the rotor are the rotor core, rotor windings, and the slip rings. Rotor core. Cylindrical rotor core is common to both squirrel cage and slip ring or wound rotors. Rotor windings. In case of squirrel cage rotor, the rotor windings consist of aluminium or copper bars of rectangular cross section, molded or inserted into the slots of the rotor core. These bars are shorted at both ends by thick copper rings. So these bars, which are rectangular in cross section, are shorted at both the ends by using thick copper rings. The rotor winding appears as a cage, and hence it is called as a squirrel cage rotor. Okay, this is how it is going to be, squirrel cage rotor. So these are rotor copper bars which are rectangular in cross section, and these two are the end rings, copper rings, to which all the rotor bars are connected. You can observe here the rotor bars are short circuited with the help of these two end rings. So this is the actual rotor construction. So you can see here, these are the rotor bars which is made up of aluminium or copper. These are the end rings. This is the shaft. This is the fan blade. Here also, it's the fan blades here. This is the laminated iron core. So the rotor slots are slightly skewed. Skewed means you can observe it is slightly placed at an angle. It is not straight, but it is slightly placed at an angle. This is known as skewing. So it is slightly skewed in order to reduce humming, to provide smoother torque, and to reduce the magnetic locking of the rotor and the stator. So hence the copper rotor bars are skewed as shown. So this is another squirrel cage. These are the stampings, rotor stampings. All such, many such types of stampings are stacked together and forms the rotor bar here. You can observe here. So this is the shaft. Now this is the cage. Because it looks like a cage, it is called as the squirrel cage rotor. So we saw the corresponding figures. So you understood? The rotor windings consist of aluminium or copper bars of rectangular cross section molded or inserted into the slots of the rotor core. In case of wound rotor or slip ring rotor, the rotor windings are similar to that of the stator. They are wound for the same number of poles as on the stator. The three-phase rotor windings are connected either in star or delta, so that the rotor acts as a short-circuited secondary in which induced currents circulate. Slip rings. Slip rings are made of brass or alloys of brass and copper. They are used in wound rotor induction motors only. They are used for inserting external resistance to the rotor windings. So this is both the rotors are present here. You can see here. This is the squirrel cage rotor. So this is the laminated core. This is the end copper bars which are short circuited onto the rotor bars. So this is the shaft, whereas this is the wound rotor. This is the laminated core. So here the slip rings will be present. So the rotor winding consists of a cylindrical core composed of steel laminations. Slots cut into the cylindrical core hold the formed coils of the wire of the rotor winding. The rotor winding consists of three single-phase windings spaced 120 electrical degrees apart. So we have completely understood the displacement when we have dealt with AC generator or the alternator. The single phase windings are connected either in star or delta. So just now we learned there will be three phases. Every phase will have two terminals or two leads. So totally 6 terminals will be coming out from a three-phase induction motor, of which only 3 terminals can be brought out, and hence the windings are connected either in star or in delta. So this is the wound rotor. Now it is usually used for large three-phase induction motors. The rotor has a winding same as the stator, and the end of each phase is connected to a slip ring. 3 brushes contact the 3 slip rings to 3 connected resistances for reduction of starting current and for speed control. Compared to squirrel cage rotors, wound rotors are expensive and require maintenance of the slip rings and brushes, and so it is not so common in industrial applications. Wound rotor induction motor was the standard form for variable speed control before the advent of motor. So this is a slip ring or phase wound rotor, or simply it is called as a wound rotor. So this is a wound rotor. You can see the slip rings here. So this is the electrical diagram of the rotor. So there are three phases. This is the R phase, Y phase, and the B phase. So it is three phases. So each one constitutes a phase winding. So R phase, Y phase, and B phase. You can observe the ends of these phase windings are brought to a common point. That's the neutral point. Now this is a star connection. The other end of the phase winding, you can observe, is connected to slip rings. So R is connected to R here. B is connected to B slip ring here, and Y is connected to Y. So R, Y, B, these are the brushes which are placed on the slip rings, and to these brushes external rheostats are connected to control the speed of the induction motor. So by varying the resistance, we can control the speed of the machine. So this is the squirrel cage rotor. Okay. So we'll just go through the difference or compare slip ring and squirrel cage rotor. Slip ring rotor consists of three-phase winding similar to stator winding. Here in squirrel cage, rotor consists of bars which are shorted at the ends with the help of end rings. Slip ring rotor construction is complicated. Squirrel cage construction is simple. In slip rings, resistance can be externally added. Whereas in squirrel cage, as it is permanently shorted, external resistances cannot be added. Slip rings and brushes are present are to add external resistance, whereas in squirrel cage, slip rings and brushes are absent. Here, the construction is delicate due to the presence of brushes and requires frequent maintenance, whereas squirrel cage induction motors are robust in construction and it is almost maintenance free. Slip ring rotors are costly, whereas squirrel cage rotors are cheaper. Only 5% of induction motors in the industry use slip ring rotor, whereas squirrel cage rotors are very common and nearly 95% of the induction motors used are of this type. Slip ring rotor has got very high starting torque, whereas squirrel cage rotor has moderate starting torque and it cannot be controlled. Rotor resistance starter can be used in slip rings. Rotor resistance starter cannot be used in squirrel cage rotors. In case of slip ring rotor, the rotor must be wound for the same number of poles as that of the stator, whereas in squirrel cage, the rotor automatically adjusts itself for the same number of poles as that of the stator. Speed control by rotor resistance method is possible in slip ring. Speed control by rotor resistance method is not possible in squirrel cage. Rotor copper losses are high in slip ring motors and hence the efficiency is less. Rotor copper losses are less in case of squirrel cage and hence they have higher efficiency. Slip ring rotors are used in lifts, hoists, cranes, elevators, compressors, etc. Squirrel cage rotors are used for lathes, drilling machines, fans, blowers, water pumps, grinders, printing machines, etc. So single-phase motors can be broadly classified as single-phase induction motor, single-phase synchronous motors, and single-phase commutator motors. Single-phase induction motors can be further classified as split-phase type, shaded pole type, and reluctance start type. Single-phase synchronous motors can be of two types, reluctance motor and hysteresis motor. And single-phase commutator motors are of different types, namely repulsion motor, repulsion induction motor, AC series motor, and universal motor. We will not be studying in detail about any of these motors since it is beyond the scope of your syllabus. Single-phase AC motors. Single-phase AC motors are manufactured in fractional kilowatt range to be operated on a single-phase supply. These motors are classified on the basis of their construction and starting methods employed. The main types of single-phase motors are induction motor, synchronous motor, and commutator motor. The applications of single-phase AC motors are found in ceiling fans, refrigerators, food mixers, hair dryers, portable drills, vacuum cleaners, washing machines, sewing machines, electric shavers, office machinery, etc. Types of single-phase induction motor. Split-phase induction motor. It is used in drilling machines, blowers, refrigerators, air conditioners, ceiling fans, etc. Capacitor start induction motors are used in lathes, drilling machines, fans, etc. Capacitor start, capacitor run induction motors are used in woodworking machinery, high pressure water pumps, vacuum pumps, air compressors, etc. Permanent split capacitor motors are used in dishwashers, washing machines, small appliances, fans, etc. And shaded pole induction motor are used in table fans, hair dryers, clocks, electric shavers, etc. So here you just have to pay attention to the applications of single phase AC motors. Types of synchronous motor. So they are of mainly two types, non-excited motors and DC excited motors. Under non-excited motors, we have reluctance motors, which are used in analog electric meters, hard disk drive motors, etc. Hysteresis motors are used in noiseless printers, hospital equipment, etc. Permanent magnet motors are used in pumps, fans, HVAC systems, automatic vending machines, barcode scanners, mixers, lawn mowers, etc. And DC excited motors are used in trains, actuators, etc. So we know that synchronous motor is also one type of AC motor. So here you pay attention to the applications of AC motors. Next is selection criteria and applications of three-phase induction motor. So the criteria for selecting the particular type of induction motor for a particular application depends on its characteristics, such as starting torque, running torque, starting current, speed, output capacity, size of the machine, power factor, construction. Construction is whether it is squirrel cage, slip ring, maintenance cost, and life of the machine. So if a particular motor has to be selected for a particular application, then depending on the application and depending on the characteristics of the machine, the selection will be done. So these are the list of characteristics. Squirrel cage induction motor. Now they have the following characteristics. They have low starting torque, about 1.5 times the full load torque, but it has very good running performance. It takes very high current, about 5 to 7 times that of the full load current. It is widely used for industrial applications when compared to slip ring induction motors. It is cheaper in cost, rugged in construction, and requires low maintenance. They run at nearly constant speed. They are suitable for applications where the drive requires constant speed, low starting torque, good running torque, and no speed control drives. So whenever an application has these requirements, then a squirrel cage induction motor will be preferred. So applications of squirrel cage induction motors are for running lathes, drilling machines, blowers, printing machines, textile motors, brake motors, flame-proof motors, fans, etc. So the important point here is they have constant speed, low starting torque, good running torque, and no speed control drives. Wound rotor or slip ring induction motor, they have high starting torque when compared to squirrel cage motors. They have good running torque, they have good speed control. They are used where power required is high, like in traction, conveyor belts, and lifts. Applications are they are employed in hoists, elevators, compressors, printing presses, large ventilating fans, centrifugal pumps, load requiring speed control such as for driving, lifts, and pumps. Okay, so let us see the characteristics and applications of wound rotor or induction motor. They have high starting torque compared to squirrel cage motors. They have good running torque. They have good speed control. They are used where power required is high, like traction and conveyor belts and lifts. So these are used in applications elevators, compressors, printing presses, large ventilating fans, centrifugal pumps, loads requiring speed control such as for driving, lifts and pumps. Advantages of three-phase motors over single-phase motors. Three-phase motors are self-starting, while single-phase motors are not self-starting. Three-phase motors are smaller in size than single-phase motors for the same output capacity. Three-phase motors have smooth running torque, while single-phase motors have a pulsating torque. Three-phase motors have better power factor and efficiency than that of single-phase motors. Three-phase motors can be built to large capacity, while single-phase motors cannot be built. Three-phase motors require less copper than single-phase motors of the same capacity. Three-phase motors are simple and rugged in construction. And also, three-phase motors have low maintenance cost. So, due to more advantages of the three-phase motors, for most industrial applications, three-phase motors are preferred when compared to single-phase motors. Nameplate details of a motor. So, nameplate details provides the specification of the motor in brief. It tells us whether it is an AC or a DC motor, whether it is single phase or three-phase motor. The HP or wattage rating of the motor will be specified. Supply voltage and frequency for which the motor is designed will be written there. RPM, that is the speed at which the motor can work safely, will be specified. And also manufacturing company's name and other details will be printed or embossed on the brass or the steel plate, and it is fixed to the stator body using rivets or screws. So in general, it's for us to make a selection of the motor by looking into the nameplate details of the motor. So you can observe the figure here. There is a nameplate detail here. So here is that of a three-phase induction motor. It is a 4-pole motor, 1 HP rating. In kilowatts, it is 0.75 kilowatts. Frequency is 50 Hertz. It will run at a speed of 1420 RPM. So it is the delta connection has an voltage of 220 to 240 volts. And the star connected rotor will have 380 to 450 volts. So like this, many details will be present on the nameplate. Here is another one. You can observe it is a 6-pole 3-phase induction motor. 60 Hertz is the frequency, 130 amps. Its RPM, the speed is 1188, date of manufacture, weight of the machine, then the HP. So the ambient temperature at which it can function efficiently. So many details like this will be present on the nameplate. So these are a few more nameplates. So this is of a single phase induction motor. It has a HP rating of 1 and kilowatt 0.75, operates at 230 volts, 5.21 amperes, 50 hertz, 1400 rotations per minute. So this is single phase, another single phase induction motor. And this is a synchronous motor nameplate. So this way, by studying the nameplate details of the motors, it will be easier to make a selection of the motor for a particular application. And also it is a ready reckoner. So we'll immediately know the technical details of the motor that is being used. Thank you. If you have any questions, you can ask.